Greetings, aspiring scientists. Welcome to my video today. It's been a little while, but I want to continue talking about stoichiometry, mole ratios, limiting reactants, and all the stuff in Reactivity 2.1. So in my previous video, we stopped somewhere in the middle of like 2.1.3, I think, and I want to finish off that and then move on to percent yield and atom economy. So let's go to my slides. So we were here in 2.1.2 and 2.1.3 talking about mole ratios and limiting reactants. We did a bunch of stuff to learn about limiting reactants and dealing with kind of solids and gases, but because the video got long, I stopped here and I want to continue here today. This is to do with solutions again and titrations. So this slide is a review from one of my previous videos, but I think it's still important to know this, so I'll review it quickly. This is a bunch of vocabulary to do with solutions, things dissolved in especially water. So a solution, the definition is a homogeneous mixture, so everything is evenly spread out and distributed. There's no like random packets of or pockets of different density in the material, it's just evenly spread out. So we have a solute dissolved in a solvent. You can see underneath that a solute is something which is dissolved, sort of the lesser amount. And the solvent, which is solvent is something which is used to dissolve. So the kind of matrix, the excess surrounding material. Most of the times it's going to be water in the questions we look at. So we can use the word dilute, that means low concentration, or the word concentrated means a higher concentration. We want to try to avoid using the words strong and weak because those have different definitions in other areas of chemistry like acid-base chemistry. So when we talk about the concentration, we can use dilute and concentrated. If we have aqueous solution, this is a solution where water is the solvent. Again, most of the time that's going to be the case here. And then the definition of concentration, the amount of solute, usually in moles per unit of volume, usually per 1 decimeter cubed of solution. So you can see that written mathematically here. Concentration equals amount of substance divided by volume of solution, where the amount of substance is the solute that is being dissolved. So we can write that as big C equals little n over big V. And the units will be moles per decimeter cubed for concentration. And that comes from moles on the top and decimeters cubed on the bottom. Very important. Then sometimes there'll be some other things here. So we'll sometimes call the concentration the molarity. Will be written with big M. And sometimes instead of writing C, we'll write square brackets. So square brackets around something A here just means the concentration of A. It's equal to the concentration of A. All right, and then just remind you about some of the glassware and stuff that we can use. There's graduated cylinders for sort of rough measurements. There's volumetric flasks for very exact measurements of sort of set volumes like 100 milliliters or 250 or 50 or 500, whatever. There'll be a line on them that you fill the thing up to. I think my picture got a little messed up here, but there'll be like a line here. You fill it up to there. If you fill it to that point, you have the volume that's written on the front. Volumetric pipette. So we can pull this up with some suction, like a rubber bulb or some other contraption. We can pull a little vacuum in this, suck up some liquid, measure how much we get, and transfer between containers that way. And there's also transfer disposable pipettes, just little disposable plastic things that don't measure well at all, but they can allow you to transfer some drops quickly. And then micropipette, the very expensive but very useful ones that can measure very low volumes, like microliters, down to microliters. And they also use a vacuum kind of suction system and disposable tips. So for sort of the questions I'm going to talk about in the next section, you can imagine somebody transferring the liquids actually using these equipment. All right. So how does this relate to moles and limiting reactants and all that? Well, let's start with practice 1. So keep in mind everything I had in my previous video about finding excess and limiting reactants and applying the amount of limiting reactant to see how much product is made or how much excess is consumed. We can do all that, but in the context of solutions, we're just going to be finding the amount of moles in a different way, usually using C equals N over V. So let's keep this in mind. C equals N over V. So the reaction of hydrochloric acid, HCl, with sodium hydroxide, NaOH, produces sodium chloride, NaCl. A 1 decimeter cubed sample of 0.5 mole per decimeter cubed HCl was mixed with an equal volume of 0.2 mole per decimeter cubed NaOH solution. Formulate a balanced chemical equation for the reaction. It shouldn't be that hard. I think we've seen this many times. HCl aqueous plus NaOH aqueous goes to salt, NaCl, aqueous, and H2O, liquid. That would just be added with the solvent and mixed together. Is this balanced? Yes. Should be already balanced. Then part B, determine the concentrations of all solutes in solution when the reaction is complete. Assume all volumes are additive. Okay, so we do have to consider what might be excess, what might be limiting. We're going to have to find the amount of moles of everything that we possibly can. So the amount of moles of HCl, we can get, if we have C equals N over V, then N equals C multiplied by V. Make sure you choose the right ones though. So the concentration of HCl is 0.5. And the concentration, or sorry, the volume of HCl was 1 decimeter cubed. So decimeter cubed units will cancel, we'll be left with moles, and we get 0.5. Okay, it's very good to know. Now, what about NaOH? I think we can just do the same. It says an equal volume of NaOH, so number of moles of NaOH also equals C times V. So we'll have 0.2 mole per decimeter cubed instead. And this will be multiplied by the volume, which was the same, 1.0 decimeter cubed. So that will come out to 0.2 moles. All right, then we can consider the ratios here. So in our balanced chemical equation, it's true that the ratio of HCl to NaOH moles is 1 to 1. So if we consider what might be limiting here, it looks like it's NaOH. So 0.2 mole of NaOH requires an equal amount of HCl. and we have more than we need. We have 0.5, so 0.5 is greater than 0.2. So pretty clearly, NaOH is limiting. It will all be used up, and there'll be some HCl remaining. So we shouldn't have any hydroxide solute ions at the end here, but we will have some HCl. How much HCl? Well, if we start with 5, and we're going to be using 0.2, we'll be left with 0.3, right? .300 mole HCl remaining. Very good to know. Then how much products can be made? We're going to be making water. We don't have to consider that as a solute, as a solvent, but we'll make some NaCl. That will need to be included to answer B fully. While the ratio of NaOH to NaCl is also 1:1. And so we will make an equal amount of NaCl in terms of moles. 0.2. Okay, but the question does say determine the concentrations. So we can't just state the moles of HCl and NaCl. We instead need the concentrations. So again, use our key equation in the top right here, C equals N over V. So for final answers, C of HCl equals N over V equals 0.3 at the top there, mole per. Now what's the volume? The final volume of mixing these two solutions, and B says assume all volumes are additive. We have 1 decimeter cubed of each solution, so the final volume here must be 2.00 decimeter cubed. Key thing to realize, check what your actual final volume will be. And that comes out to 0.150 mole per decimeter cubed. Okay, so 0.150. Then the concentration of the other solute, NaCl, also required. This equals N over V, so that is number of moles that we produced. That's on the far right side, 0.2. In the same volume, same final volume of 2 decimeter cubed. And that comes out to a slightly different number, 0.100. Okay, so those are the final answers. Concentration of HCl solute, which probably exists as H plus and Cl minus, and then the concentration of NaCl, which probably exists as Na plus and Cl minus. All right, that's good. More practice then, move on. Practice 2, sulfur dioxide SO2 can react with water H2O to produce sulfurous acid H2SO3. Sulfur dioxide can be absorbed by alkaline solutions, such as with NaOH, to produce salts of sulfurous acid, such as Na2SO3, sodium sulfite. Formulate equations for the formation of sulfurous acid. There should be an R there. And its neutralization with sodium hydroxide. We can do that first, not too difficult. I think they're simple equations. So first, sulfurous acid is just SO2 gas plus water. Goes to H2SO3 aqueous. That aqueous acid. And this is already balanced. We're just sort of combining these together. A plus B goes to C. But we also need the neutralization of that acid with sodium hydroxide. So that will be acid plus base, H2SO3 aqueous, plus NaOH, aqueous, goes to our sulfite salt, sodium. We'll need 2 of those to balance the sulfite 2- charge. Aqueous and water. Okay, is this balanced? No. A sulfurous acid has 2 protons, 2 H's on it, and they will each need to combine with an OH from sodium hydroxide to be neutralized. So we'll need 2 of these for sure. We also need those 2 sodiums to balance. And this will instead produce 2 water molecules instead of just 1. So that's the way to balance this. All right. Easy part done, but absolutely critical to get a balanced chemical equation like this. Now determine the concentrations of all solutes in a solution when 2.84 decimeters cubed of sulfur dioxide is absorbed by 2 decimeters cubed of 0.4 mole per decimeter cubed solution of sodium hydroxide at STP. Assume that the absorption does not change the volume of the solution. So this is very similar to the previous question again. So again, we want to just find the moles of everything that we possibly can and then try to find out what's limiting here. So sulfur dioxide has a volume at STP. So NSO2 we can find with the molar volume, V over Vm. 2.84 decimeter cubed divided by 22.7 decimeter cubed per mole. And that comes out to 0.125 moles. Very good to know. And what else? Well, the first reaction is that this reacts with water, but we have a solution of water that we can basically just assume is excess. Compared to 2.84 decimeters cubed of sulfur dioxide, we can assume that there's more than enough water to react with this. So SO2 we can just guarantee is limiting. 2.00 decimeter cubed of water. Well, that's way more than we need. That's fine. So how much H2SO3 can be made? The ratio of SO2 to H2SO3 is 1:1. The nicest of ratios. So we'll make exactly that much. 0.125 mole of H2SO3 is made. All right, so that can bring us to the second equation here, where our H2SO3 will react and neutralize with the base. And I'm still going to assume that our acid here is limiting. It looks like we have plenty of base, but we also have a ratio of 1 to 2. We would need twice as much base. So I'm just going to move up to the top here and consider that ratio. So the mole ratio in chemical equation 2 between H2SO3 and NaOH is 1 to 2. So we need twice as much NaOH. So 2 over 1, but I'll just write 2 here. 2 times 0.125 is required. That comes out to 0.250. We need 0.250 moles of NaOH required. Do we have that? Well, now might be a good time. Probably should have done it earlier, but we can find out exactly how many moles of sodium hydroxide we might have, but I think it will be enough. N equals C times V. Choose the right ones though, so 0.4 mole per decimeter cubed. Multiplied by the volume, 2 decimeter cubed. But you can see this comes out to 0.8. So we have much more than enough, more than twice as much as we need, more than 3 times as much as we need. So H2SO3 will be limiting in the second equation here. Now we just need to find out how much sodium hydroxide will be remaining and how much sodium sulfite will be produced. So for remaining NaOH, excuse me, I'm just going to be writing all over the place, trying to find some space, but I'll try to label things. So the remaining NaOH will just be the total amount that's in the solution, 0.8, minus the amount required, 0.25. And that comes out to 0.550 moles. Very good to know. And then we need to know how much Na2SO3 will be produced. So I'll try to write that on the right here. Sorry for going all over the place. So Na2SO3 produced. What's the ratio between our limiting reactant? It's 1 to 1, 1 to 1 ratio. So we'll also make 0.125 mole produced. Okay, and then I'll try to write the final answers on the left here. So again, this asks for concentrations of all solutes, not just amount of moles. We can assume our volume does not change by absorbing this gas, so we can just use a volume of 2 decimeters cubed. All right, so the concentration of NaOH remaining equals N over V. This will be 0.550 divided by 2 decimeter cubed. So that's 0.275 mole per decimeter cubed as the final answer for NaOH in solution. And then concentration of Na2SO3 is also equal to N over V. We've got 0.125 divided by the final volume, which is the same as before, 2 decimeter cubed. And that comes out to much less, 0.0625. Mole per decimeter cubed. Final answers for all these solutes remaining in solution. So I find that a little bit boring and tiresome. I'm sure many of you do as well, but it's important to do it quickly, concisely, without making mistakes. Make sure you can get the same answers. All right, good. I think more practice then. Practice 3, 20 centimeter cubed of sulfuric acid solution, H2SO4, of unknown concentration was titrated with 0.2 mole per decimeter cubed solution of sodium hydroxide, NaOH, in the presence of an acid-base indicator. The color change was observed when 14.3 centimeters cubed of the sodium hydroxide solution was added. So there's some key information here. You need to know a little bit about titrations. I have previous videos on that from many months ago, but what you need to know is that when the color change of an indicator happens in a titration between acids and bases like this, it means that you've achieved complete neutralization. The reaction is complete, essentially. So in a question like this, where a color change was observed, this means the reaction is perfectly complete and there will be no limiting reactant. Okay, because you stop as soon as you perfectly complete the reaction and add the correct number of moles. You might have some extra excess in your burette that's above the mixture, but you're not actually going to add it, so you don't consider it. All right, but we can still do this question. It's very similar. Formulate a balanced chemical equation for this reaction. Not too difficult. We've got strong acid H2SO4, aqueous, mixing with NaOH, aqueous, going to sodium sulfate this time, Na2SO4, aqueous, and water. Is this balanced? No, we need 2 sodiums, and we need to react with those 2 protons in sulfuric acid. This will produce 2 waters, 1 for each proton. But that's essentially it. Liquid water. All right, part B then, determine the concentration of the sulfuric acid solution. Remember at the beginning it said it's unknown. So what we want to do is find out how many moles of sodium hydroxide was required to complete this reaction, and we can do that fairly easily. Moles of NaOH is equal to C times V. Just choose the right values. The concentration of the sodium hydroxide solution is 0.2 mole per decimeter cubed. And the amount of volume was 14.3 centimeters cubed. I don't want to work with centimeters cubed. We need to cancel out decimeters cubed. So we'll write this in decimeters cubed, 0.0143. Divide that by 1,000. Okay, that will come out to a small amount of moles, 2.86 times 10 to the minus 3. Write that in scientific notation, although you don't really have to. Okay, so that's how many moles of NaOH reacted here. What about sulfuric acid then? We need to consider the ratio. Moles of NaOH to moles of H2SO4 in our balanced chemical equation is 2 to 1. So we will be reacting with half as much. 1/2 times our amount of sodium hydroxide again, as I said, there's no limiting amount, so we can just use sodium hydroxide here. And that gives us 1.43 times 10 to the minus 3. Of H2SO4, which reacted. Okay, and then I think just we need to finally find the concentration of that sulfuric acid. Again, go back to the roots, C equals N/V. So the concentration of sulfuric acid, H2SO4, is equal to its moles that we just calculated, 1.43 times 10 to the minus 3. Divided by its volume. It says somebody had about 20 milliliters, 20 centimeters cubed. Again, we want concentrations in decimeters cubed though. So divided by 1,000, 0.0200 decimeter cubed. And that comes out to 0.0715 mole per decimeter cubed. Done. All right, I think I have one more practice of similar things here. Practice 4, complete neutralization of 10 centimeters cubed of sodium hydroxide solution required 9.1 centimeters cubed of 0.5 mole per decimeter cubed solution of hydrochloric acid. Determine the concentration of sodium hydroxide. Very similar here. We'll just draw a chemical equation. I think we've already seen this. This will be HCl plus NaOH. Goes to NaCl and water. And just find moles of whatever we can. So moles of HCl. C times V. Choose the right values though. Concentration of HCl is 0.5. And the volume, 9.1 centimeters cubed. Again, I don't want that. Divide by 1,000, 0.00910 decimeter cubed. And that comes out to 4.55 times 10 to the minus 3 moles. All right, and keep in mind here that this says complete neutralization again. So we won't have a limiting reactant here. We'll just have exactly the amount required for complete reaction, complete neutralization. So we can just assume that we're dealing with an amount equal to this amount of HCl for the NaOH, but we do have to consider mole ratios. The ratio of HCl to NaOH is once again 1 to 1. So the same amount of moles of NaOH must react. And then we can find the concentration. So the concentration of NaOH equals N over V. We've got 4.55 times 10 to the minus 3 moles in some volume. It's 10 centimeters cubed. You don't want to work with centimeters cubed, so divide by 1,000. 0, 1, 0, 0 decimeter cubed. And that comes out to 0.455 mole per decimeter cubed. Done. All right, so you need to get pretty quick at this. You can kind of maybe go a little bit faster than I do and skip some steps writing these ratios if you're really sure about it. But as you're practicing, I still recommend you write all this, write all the units, and all the ratios. All right, so that brings us to the end of this solution section. I want to go on to 2.1.4 then, the reaction yield. If you've done any kind of lab reports in your class already, you probably have come across this, but I'll remind you, the law of conservation of mass is a thing that exists. Total mass of reactants must be equal to the total mass of products in a chemical reaction like this. Mass cannot be created or destroyed, can't suddenly disappear. But sometimes this rule will appear to be broken when accounting for mass is not done perfectly. So you might calculate that you should get 5 grams of something, but when you go to measure it, you get 4.87. Well, what happened to those other 0.13 grams? Well, things like gases can escape if you don't have a perfectly closed and isolated system. You might be washing, you might be recrystallizing, you have all these solvents going through. Every time those will carry a small percent, or sometimes a large percent of your mixture away, dissolve it slightly. Bits of solid or liquid stick to the tools and containers that you're using. So you probably know when you're moving things around with filter paper, with beakers, with flasks, with spoons, you'll never get 100% off. Sometimes it gets stuck, so you lose a little bit of mass that way, a little bit of moles. So percentage yield. When experiments are done in reality, the actual experimental yield almost never matches the theoretical yield exactly. It may be lower due to lost materials, some of the reasons I mentioned on the previous slide, or it could be higher sometimes. That's often due to water not being dried properly, or other solvents, or other impurities, possible side products. In such cases, we're interested in calculating the percentage yield. It can be calculated with the number of moles or the mass of products, so that's a good thing to know. If you only have one or the other, don't panic. Don't necessarily convert it either. You don't need to. You can just use whichever one you have access to in the moment. And the way to do it is percentage yield equals experimental amount divided by theoretical amount. You can use N for moles or M for mass. Both work because they're proportional to each other. But remember that your experimental one is what's measured in the lab in the real situation. And then the theoretical is at the bottom. That will be calculated from your balanced chemical equation and the mole ratios relating to the limiting reagent. So practice: mixture of 10 grams of calcium metal and 9.62 grams of sulfur were heated for some time to produce 17.0 grams of calcium sulfide, CaS. Calculate the theoretical yield of CaS. All right, first balanced chemical equation we should have. I think it's just calcium plus sulfur goes to calcium sulfide. Solids goes to another solid. Everything 1 to 1. But we need to find moles, so moles of calcium. We have a mass, so mass over molar mass. Just choose the right ones. We've got 10 grams. Calcium on the periodic table, 40.08 gram per mole. So that comes out to 0.25 moles. And then we'll need to do the same for sulfur. Moles of sulfur equals mass over molar mass. We've got 9.62 grams divided by 32.06 gram per mole. Okay, that comes out to 0.3. So considering that everything is 1 to 1 here, I hope that you can just see without all the calculations we've done in previous questions that if things are 1 to 1 here, calcium is limiting. It requires the same amount. And we have more than enough sulfur. Sulfur is excess. Okay. So we'll just focus on calcium to predict the theoretical yield. So I'll just move up to the top here. So the ratio of calcium moles to calcium sulfide, our desired product, is 1 to 1. So we can also make 0.250 mole can theoretically be made. So that is in fact our theoretical yield in the form of the amount of moles. Now, calculate the percentage yield of CaS in this case. So percent yield from my previous slide is equal to experimental amount Experimental yield over theoretical yield times 100%. In this case, our experimental was given in the question, however, it was in grams, right? So I'd rather just convert that to moles. Moles of CAS is equal to mass over molar mass, 17.0 grams, divided by molar mass of calcium sulfide, 1 calcium and 1 sulfur, is about 72.14 gram per mole. So this comes out to 0.236 moles. So I'll put that in for my experimental yield in terms of moles. And then theoretical yield should have been 0.25 on the top there. But what we get is this is about 94.3% yield, which is very high. If you can get that, you're generally very happy. They're more commonly 60 or 70 or 50-ish. All right, that's good. Maybe another practice. Calculate the theoretical percentage yields of the reaction between 9.443 grams of aluminum and 7.945 decimeters cubed at STP of oxygen gas that produced 17.13 grams of aluminum oxide. I think there should be an and here, theoretical and then percentage yield, so it's similar to the previous question. All right, let's do that. So first thing, balanced chemical equation. We know what the starting materials and products should be. So we'll have aluminum solid reacting with oxygen gas, going to aluminum oxide Al2O3, solid. To balance this, I think we're going to need 3 oxygens, we're going to need 2 Al2O3, and we're going to need 4 aluminum metal atoms. So our ratio is 4 to 3 to 2, a little bit more complicated than the previous ones. But steps you'll follow are essentially the same. We want number of moles of whatever we can find. So aluminum, mass over molar mass. This is 9.443 grams. Divide by molar mass of aluminum from the periodic table, 26.98. So we are working with 0.35. Moles of aluminum. What about oxygen? For this, we don't have a mass. We instead have a volume at STP, so we'll use volume over molar volume. Best way. That will be 7.945 decimeters cubed. Divided by 22.7 decimeters cubed per mole from the data book. And that comes out also to 0.35. I'll just say that this, from the data book, had 4 sig figs so that we can keep 4 in all the numbers. So you might look at this and say, oh, there's equal amounts, so there's no limiting reagent. not true though, because our balanced chemical equation no longer has 1-to-1 ratios. It's 4-to-3 for aluminum to O2. So the moles of aluminum to moles of O2 is equal to 4-to-3. So what can we say about that? If we consider aluminum might be limiting, 0.3500 mole of aluminum requires, target on the top of the fraction, 3/4 multiplied by the amount of the proposed limiting reactant, 0.350, and that equals about 0.2625 mole of O2. Do we have that much O2? Yes, we've got more than enough. So 0.3500 is greater than 0.2625. Considering O2 here, so we can say that O2 is excess and aluminum is limiting. So we'll base everything else on aluminum from now on. So for the theoretical yield, use the limiting reagent amount. And what's the ratio between aluminum and aluminum oxide? It's 4-to-2, which is the same as 2-to-1. Just reduce it down to the simplest form of that ratio. So how much can be made? Our target is now aluminum oxide, so 1/2 times the amount of limiting reactant, 0.3500 that we have. That's 0.1750. Mole of aluminum oxide, Al2O3, can be made. Okay, so that's like the theoretical yield, the first part of that, but we also need the percentage yield because we do have an experimental amount that was produced, 17.13 grams. So I'll just move up to the top here. Experimental amount. We want to find out how many moles this is so that we can compare it with the moles in the theoretical. So moles of Al2O3 equals mass over molar mass, 17.13 grams. And molar mass, Al2O3, 2 aluminums, 3 oxygens. It's about 101.96 gram per mole. So this comes out to 0.168. Experimental amount. So that's slightly less than a theoretical amount, right? So whatever happened in this reaction, somebody lost some mass, either from solid being stuck to containers or gas escaping, whatever. So final answer, try to do on the top left here, percent yield equals experimental, or sometimes called actual, divided by theoretical. And so this is equal to 0.168 mole divided by theoretical at the very bottom, 0.175. And that is 96%. Pretty exactly, 96.00%, we'll say. Final answer for that percentage yield. Okay. So kind of a lot of work, but it's what you need to do. Find limiting, find the amount of products theoretically produced, check how much was actually produced, find the percentage. All right, moving on. Last section here, 2.1.5, green chemistry and atom economy. So some points about green chemistry. Up until recently, yield, purity, and profits, economic, monetary profits, were the main considerations of most chemical companies. But the idea of green chemistry is a more recent idea, the idea that we need to consider all aspects of a chemical process and improve them to maintain a sustainable and comfortable planet to live on. So there's many things to consider, but here are some of the key ones we might consider at the high school level. Organic solvents, things like, hexane, octane, ethyl acetate, acetone. These allow reactions to happen quickly. We can dissolve things, make homogeneous solutions, have high reaction rates, but they're removed and thrown away afterwards. They're just usually evaporated off. This causes problems and is very wasteful. Next, renewable starting materials. Some materials are in limited supply and cannot be produced again easily after use. For example, fossil fuels, petrochemicals. Are there any renewable options, such as maybe alcohols from our biofuels section? Mild reaction conditions then. So the rest of your reaction might be pretty green and efficient, but what if you need to use a lot of heat to get your reaction going, or strong acid, very large or rare catalysts? These are examples of things that might require energy and effort that we have to consider every time we do a reaction. What else? Catalyzed reactions. If you can catalyze a reaction to be done quicker at lower temperatures, that often requires less time and less energy. It's more efficient overall. And then usage of all products. If all the products of your chemical reaction are useful in some way, you don't have to throw them away or dispose of them or worry about their toxicity maybe. So it's better if we can have useful products. So that brings us to the idea of atom economy. It's a useful method of calculation to estimate the efficiency of a reaction. It's not the only measure of efficiency. Percent yield that we just looked at is another example of the efficiency of a reaction. But atom economy is sort of a more fundamental consideration, core consideration of how to envision the wastefulness of what you're trying to do. It's the ratio of your useful target product to the combined molar mass of all the starting materials. And through conservation of mass, you can also consider the molar mass of all products. That should be the same. But stoichiometric coefficients must also be included as multipliers in this equation. But essentially, percent atom economy is the mass or molar mass, atomic mass of your target products over the molar mass of the starting materials, total starting materials, or total products, times 100%. And sometimes we'll also be considering the molar mass or molecular weight of solvents or catalysts that are involved. I've seen some practice questions involve this, but most really don't. I wouldn't worry about it too much. These are often input to calculations as well. All right, so some practice. Dimethyl carbonate, CH3O2CO, is a non-toxic and highly efficient green solvent. Calculate the percentage atom economy for the synthesis of dimethyl carbonate by the following reaction. So you can either do the total mass of reactants or the total mass of products. As I said, there must be conservation. But because I'm going to be also considering the target product, I'll instead choose to do the total mass of all products in terms of molecular weight, not in terms of grams, right? So this will be equal to 2 water, so that's 2 times 1.01 for hydrogen and 16.00 for oxygen. And then the dimethyl carbonate, we make 2 of those as well, but we'll have a bunch of carbons. There's 3 carbons total in that. So 3 times 12.01 plus the hydrogens, there's 6 of those. 6 times 1.01, and we've got oxygens, there's 3 of those, 3 times 16. So I just multiply these through a little bit. On the left side here we have 36.04 atomic mass units, and then on the right we've got 180.16. So in total, it's 216.22. Now, mass of target products, which is dimethyl carbonate, mass of target products is, that's what's on the far right side of the previous equation, so that was 180.16. That's why I chose to find the mass of all products. So I can take a little shortcut there. So percent atom economy is equal to the molecular weight or molar mass of target products over the total mass of the reaction mixture. So that equals 180.16 for the target, divided by 216.22 for the total. And these are both times 100%. I shouldn't forget that. And that comes out to 83.323, basically 83%. Okay, so that's how it's done. Not too difficult. There's no limiting or excess reagents in this. It's just looking really at the theoretical balanced chemical equation, finding out what amount of wastefulness and what amount of actual target products will be produced as a percentage. Okay, and the final thing here, final practice question for today, I think. Dimethyl carbonate can be used to convert phenylamine, C6H5NH2, into N-methylphenylamine, C6H5NHCH3. Byproducts of this reaction are methanol and carbon dioxide. Determine the balanced chemical equation for this reaction and its atom economy. All right, so we've got dimethyl carbonate, CH3, 2, CO. I don't know what this is. We'll say it's a liquid plus phenylamine, C6H5NH2. I think liquid. This creates the target product, C6H5NHCH3, probably liquid, but side products, byproducts are methanol, that's CH3OH, liquid, and CO2, gas. Okay, you might want to check if that's balanced, but I've checked it and it is actually already balanced. Good to know. So what's the atom economy of this? Our target is the N-methylphenylamine. So I'd rather just find the total mass of all the products here. I don't have much space, so I'm going to do a little bit of shortcuts, but hopefully you can follow what I'm doing. The total mass is equal to the N-methylphenylamine, which is about 107.17, plus the methanol, that's about 32.05, and the CO2, it's about 44.01. Okay, so I took some shortcuts there with calculating all these masses, but just so you know, this is this, methanol is here, and CO2 is here. In total, this equals about 183.23. That's our total mass of the reaction mixture. And our target desired product is this one, 107.17. So percent atom economy, I'll draw at the top here. Equals our target product, 107.17, divided by the total mass, 183.23 times 100%. So that comes out to 58.489. And that's not really great. A lot of the mass of our mixture is being wasted as CO2 and methanol that we're going to have to deal with at the end. Find something to do with it or find somewhere to put it. But let's do part B. Considering the equation for the formation of dimethyl carbonate, how could the atom economy for the formation of N-methylphenylamine be improved? So the formation of dimethyl carbonate, I will remind you, was on the previous slide. It is here, right? Methanol plus CO2 and oxygen goes to dimethyl carbonate and water. So the answer that I think they're looking for here is use the methanol and CO2 to produce dimethyl carbonate again. That way, only like the H2O from the first equation would actually be kind of a waste product. We don't really have anything else to do with that, but H2O as waste products go is not that bad. If we do this, atom economy, especially for the second reaction here, will be increased. because we're actually finding a legitimate use for the products. Now all the products can become target useful, usable products. All right, so as long as you're not just disposing of the products here, if they are useful in some way to your process, you can consider them as useful and increase your atom economy. All right, so that brings us to green chemistry. Just some final points I'd like to mention. The immediate price in terms of money and time and resources of designing and implementing a green chemistry reaction is often high. You have to avoid certain solvents, certain energies and temperatures. So many organizations, I think you'll find, avoid it or just don't bother thinking about it. However, consider the cost of poisoning a whole lake or some environment, creating a hole in the ozone layer that allows harmful UV light to come through, making farmland infertile due to chemical wastes. We can't grow crops there anymore. The cost of fixing those large environmental issues will be far, far greater than the cost of switching to a green chemistry method for a mass production of some resource. So we'd really better consider green chemistry reactions. The entire life cycle of a product must also be considered. Where did the starting materials come from? What kind of conditions does the reaction require? Where do all the materials end up going? How are they used in the end, or how are they thrown away? Many single chemical reactions, you can just look at one balanced chemical equation. You say, okay, that's good, that's efficient, that's green, that has high yield, that has low temperature conditions. But you need to consider how everything in that comes into play. How do each starting material get to that point? Where do the products go in the end? You might have a trail of toxicity and or long future of pollution problems ahead of some of these materials. So I'd recommend, deeply investigating as much as possible. We're not really going to do that in high school. This is more for your future career, I think, but something to think about. So that brings us to the end of this Reactivity 2.1. The guiding question was, how are chemical equations used to calculate reacting ratios? Hopefully you can answer that now. The balanced chemical equation is so important. That represents at the atomic scale how do individual atoms and molecules come together. Then you could say, okay, if that happens twice or 5 times or 10 times, you start thinking about how many moles and how many grams and other versions of amounts and masses can be brought together in this way. Which one of them will be all used up, the limiting reactant, which will be in excess and have some remaining. How does the limiting reactant tell you how much products can be made? It's all in the mole ratios that come from the stoichiometric coefficients, the numbers in front of the chemicals in the balanced chemical equation. Okay, hopefully you know how to do this now. I've done so many examples. You can always go back and watch them again. But good luck studying and practicing. Good luck on your exams. That's all for today. Next time we'll do rates of reaction. See you next time. Bye-bye.